Hey everyone, we're going to talk about integrated rate laws to start with and continue on kind of our discussion of rate laws. So integrated rate laws allow us to solve for some sort of concentration at a particular point in time. We're going to walk through, we've got first order, second order, and zero order. So the rate up until now was equal to K times the concentration A for a particular reaction, like if we have A going to some kind of products. And we also had the rate here. But if you integrate this, and this is in a calculus-based class, but you end up with this reaction right here, where the ln of AT is equal to negative KT plus the ln of A naught. And again, that's for first order. We're going to have different integrated rate laws for different order reactions. So this maybe you should recognize anytime you have something equals something plus something, ask yourself if it might fit into y equals mx plus b. Because if we were to draw this out, and do a graph, the y automatically we know will be the ln of A at a particular time. So the concentration of A at a particular time. M is going to be the slope of the line. Our t time is going to be our x value. And then B is obviously what up or down movement, or sometimes we kind of look at it almost like an error if it doesn't go through 0, 0. But our M in this particular case is negative K. Okay, this is cool because if we know the concentration of A, so we have some kind of reaction. Let's say we're looking at hydrogen peroxide. If you've ever seen elephant toothpaste, you've seen this reaction where hydrogen peroxide decomposes into oxygen and water, and it gets all bubbly. So if you were to watch that reaction occur and check the concentration of hydrogen peroxide at any given time, and plot the ln versus this, assuming it was a first order reaction, it would look like this, and the slope would actually tell you the K of the reaction, particularly the negative K, but you could take the absolute value of that and get the K. All right, so let's say you actually did that. On the next page, it says, let's say you plotted it for SO2 Cl2, and you found the rate constant was this. In other words, K, or your slope equals negative K, would have been negative 2.90 times 10 to the negative 4 inverse seconds. If you're like me, you like to write it like that instead of using scientific notation when you're talking about smaller ones. It helps me see things a little better. All right, so it says you plotted the concentration decomposition of SO2, Cl2, and you found that its rate constant was this. It said if the reaction is carried out at the same temperature and the initial concentration is 0.225, what is a concentration after 865 seconds? All right, so we've got this first order rate law. We know it's ln of A at a particular time equals negative KT plus ln of A naught, which means initial. All right, so we're solving for this. It asks for what is the concentration. So it asks for this, that's our question mark. Our K we solved by plotting this. This is how we got this K. Also tells us that we found it was that. So this is 0.000290. And our initial concentration was 0.225, and finally our temperature, or our time, excuse me, was 865 seconds. I'm gonna pull a calculator because this was in your book, but your book had the wrong answer, the wrong calculation, so I want to make sure that we do this all together because oftentimes we haven't seen log for a while, natural log specifically. There's a difference between those two things. Okay, so I'm solving for this. I'm going to go ahead and plug in all my numbers. I've got the ln of AT equals negative 0.000290 plus ELN times 865 plus the ln of 0.225. All right, so step number one, I'm going to take the natural log of 0.225. To do that, I don't know, I've never used this one. Oh, yep, you hit log first. So ln 0.225, close its parentheses, hit enter. I get negative 1.49. So again, make sure you're using the proper ln right here and not the log. Log is log base 10. That's not what we want. Okay, and then let's multiply those two together. So I got negative 0.00029 times 865. And that gives me negative 0.25085. So now I'm just going to take this minus that. I usually like to keep more numbers than I did. And I get negative 1.741. Now, right now we have the ln, the concentration of A at a particular time equals negative 1.741. In order to get rid of that, we want to use E, the inverse log, right? And that's right here. So in order to do that, reduce second E to the negative 1.741, close the parentheses. And I find, I'm going to do a better job here. So when you take E to the natural log, it cancels that out. So essentially what we get is AT equals E to negative 1.741 right there. And that equals the calculation we did, 0.175. So again, I did second natural log this because I see the E right there. And that's how I was able to get my concentration. All right. So that's how we solve that equation, and I wanted to do it mainly so that you got used to using natural logs again. And E. All right. So that was first order. Second order works the same way. If you remember, second order rate law is K times A squared. And through the integrated rate law, you get something like this. Also, this would be like y equals mx plus b. And if you plotted this sucker out, on our y, we would want 1 over the concentration of A at a particular time. Our slope is positive K. And T, time in seconds, would be our x. Again, that's because that's y, that's m, that's x, and that's b. And you'd get a beautiful straight line if it is in fact second order. And last but not least, we have zero order. Kind of similar. Y equals mx plus b. But in this case, I see that the k is negative, so that means we'll probably get a negative slope. Our y is the concentration of A at a particular time, and our x is, again, time in seconds. And our slope would be negative k. All right, so the point of this stuff is, one, to just kind of reinforce the concept that oftentimes we can graph things to get particular answers. So anytime we graph the y versus the x, we can get this slope, which happens to be k, and that's really cool. And the second thing I want you to pay attention to is the fact that there's different integrated rate laws. Sorry, on the other one, there's another one. Different integrated rate laws for different orders. All right, moving on. Let's look at half-life. So half-life of caffeine, it says, is 5 hours. So what half-life is the amount of time required for something's concentration to be half of what it was. So, for example, if you go and drink 200 milligrams of coffee at 8 a.m., by 1 p.m., which is 5 hours later, that will now be in your body about 100 milligrams of coffee. And then by 6 p.m., you still have 50 milligrams of that caffeine in your body, and then continue on and on and on. So even the next day, you'll have a smidgen left of what you originally had. So that's half-life. There are 3 different equations for half-life, and these will be given to you on the exam. Not only will they be given to you, you'll also be told, usually in a question relating to half-life, which order it is. So in this particular case, it says, in this example, molecular iodine dissociates at 623 Kelvin with first order rate constant of this. What is the half-life of the reaction? Well, it said first order, so my initial thought is I better write that first order equation. The next thing is to pay attention to the fact that this is the half-life time, so the amount of time it takes to be halved. Remember, with caffeine, it was 5 hours. This number is given to you, and this is K. This is the rate constant K, so not Kelvin. So be careful. You pay attention to capital and lowercase k's. This is lowercase, as is this, as is this. Okay. So it's just saying at this particular time. It's just some background information, or at this particular temperature. It's just some background information. All right, so now we take 0.693 and divide it by our 0.271 inverse seconds, which actually brings the seconds up to the forefront. And I get, if I take, let's do it, 0.693 divided by 0.271, I get an answer of 2.56 seconds. So that would be the half-life of molecular iodine dissociating. All right, this table, I just thought it was a good summary table. It has a lot of information in it, and it might really help you guys. So this will be given on the exam. Okay, so I will definitely give you this on the exam. I will also give you this. A lot of things to give you. We might have to have a whole page. I might have to reduce the amount of memes I give you. I don't want to do that. All right, the effective temperature on a reaction, or on reactions, and the rate at which they occur. So, rate is highly dependent on temperature. Generally, that's because it helps break, temperature is indicative that heat has been added, and heat helps break bonds. Not always, but usually. And it's the person who figured this out, his name was Svante Arrhenius. He was a Swedish chemist, and he determined that, hey, if we adjust the temperature, we actually change the rate constant. So the rate constant is temperature dependent. It will change as you change the temperature of a reaction. And that should hopefully make a little bit of sense. But let's go through each of these just a second. So E sub A is the activation energy. That's the amount of energy required for the reaction to occur. You'll see this a lot, and so it's kind of important that you understand this concept. So maybe now is the time to take time to understand it. It's just the amount of energy to get over a hump. So the example I gave in class is waking up in the morning, you're laying in bed. The rest of your day tends to go pretty easy, but one of the hardest parts of the day can be when you're getting out of bed or having to wake up and getting that activation energy and getting enough energy to overcome that hump, because once your feet are on the ground, the rest of the day can go smoothly. And that's exactly the same with reactions. It requires a certain amount of energy for the reaction to occur, and once that occurs, it can fall back down. Now, this happens to be an exothermic reaction. The products could have ended here just as well. So this, don't be too frustrated by this. What's important is that the energy from where we started to the top of this hump, that whole thing, is called the activation energy. That's the E sub A. The frequency factor is essentially how many times a reactants kind of get up there and are hitting each other. And the exponential factor is a number between 0 and 1 that represents the amount of times they actually have enough energy. In other words, it's almost like a decimal percent. So for example, if your frequency factor is 100, meaning 100 times in a reaction your molecules are hitting each other and able to overcome a barrier, if your exponential factor is only 0.8, then that means only 80 of those molecules will actually go through. So if this was our frequency factor, that would be our exponential factor, telling us only about 80 can actually proceed all the way through to the products. All right, so this is another form of the Arrhenius equation. Essentially, they just took ln to get rid of that E and rearranged it to make it look like this. So this is the exact same equation as this, but this is more user-friendly form, I think. Hey, wait a second, I got something equals something times something plus something. That looks like a y equals mx plus b to me if I've ever seen one. I don't know about you, but it does. So you could plot the ln of k on the y-axis versus 1 over temperature, and this is what Arrhenius did. And by doing that, you get a slope that has the activation energy. And I think that is so cool. But that's how you solve for things. Okay, so when given 2 points, you can use this form of the Arrhenius equation. It essentially compares data points. So if you're given 2 different points, like 2 temperatures, 2 Ks, 2, actually that's about all you can do for the 2s. You would solve for something. Let's do this. So it says consider this reaction, and this is the other one given. I will be giving you that. And it gives us, it says that the reaction at 701 Kelvin has a K of 2.57. And then at a higher temperature, 895, it has a higher K of 567. And it says use that information to find the activation energy for the reaction, which we can do because we look at this and we say, oh, it's got 2 temperatures, or oh, it's got 2 Ks. I know I've got to use this guy. So we're just going to kind of plug and chug. In fact, maybe before I write it, just to save some room, let's go ahead and figure this out. I'm going to call this first set of data 1 and the second set of data 2. So this would be my T1, this would be my K1. This would be my T2, and this would be my K2. And from there, I can figure it out. So we have ln of our K2, which was 567. I'm going to avoid writing units just to kind of clear things up a little bit, clean them up, divided by our K1, which was 2.57, equals our E sub A, which we are solving. R is always 8.314 joules over mole Kelvin, the quantity mole times Kelvin. So I'm going to 314. And then we got our temperature. 1 over our initial temperature minus 1 over our final temperature All right, let's go ahead and do this. I'm going to go ahead and do it for you on the calculator because hopefully that helps a little bit. Let's move that over. There we go. Okay, so I'm going to say 1 divided by 701. I'm going to do this quantity first, and then I'm going to do this, and I'm going to divide each one by that. So 1 divided by 701 minus, now I have to do in parentheses, 1 divided by 895, and parentheses. And I usually like to do this in one fell swoop on my calculator, but I want to show you these intermediate steps in case you want help on that. Okay, so this quantity right here equals that. On the other side, I'm going to do the natural log of 567 divided by 2.57 in parentheses. And I get 5.39 All right, just to clear everything up here, right now I have 5.3965 equals E sub A over 8.314 times 0.000309.215, I think. All right, I'm sorry if I'm off by like a little number. Now I'm going to multiply that by 8.314. So I multiply that by that, and that gets rid of that. And then I'm going to divide both sides by the 0.000309.215. And that's going to solve for my E sub A. And I get a big number, 145,097 joules. The reason I knew it was joules was because this was joule per mole K, which cancels out with the K's that come from here. And the mole did not cancel, just kidding. This is going to be per mole. Oftentimes we want it in kilojoules per mole, and I feel like that question should have asked for that. But usually if you're getting a number that's like 100,000 above, you're going to want to put it in kilojoules. That would just be 145 kilojoules per mole. And that would be our answer. All right, so we talked about collision frequency and orientation having to do with rate. And that's included in A. So A has orientation factor and collision frequency. Let's talk about orientation factor. Collision frequency is how often things are colliding. That again, you can enhance that depending on the concentration, etc. But the orientation factor I think is kind of interesting. So let's say we have like H plus I. So some kind of monoatomic gas forming HI. Essentially you've got like some kind of sphere, some kind of other sphere, and I call them spheres, they're really atoms with electrons moving. They're like moving blobs really. But if this one hits this one, they're going to form an HI. All right, so this can hit, this iodide can hit anywhere it wants to. This monoatomic iodine can hit anywhere it wants to on the hydrogen, and that hydrogen can hit anywhere it wants to on the iodine. So it doesn't matter at all. The orientation isn't important. As long as they hit each other, they can form this. But let's talk about HCl. These guys, if they hit the way they are, this Cl will hit this hydrogen, for example, and that's not helpful at all. It's not going to create this. We need the hydrogen to hit the hydrogen and the chlorine to hit the chlorine, for example. So the only way that can happen is this one's flipped around and going in this way. So if we flip this around, for example, then this hydrogen can hit that hydrogen, and that chlorine can eventually hit that chlorine because they'll be without their hydrogens. And that's glorious. Whoops, I should have left that HCl. But what it shows is that this has a low orientation factor. And this one, which is really easy for them to hit each other, has a high orientation factor. All right, so let's move on. All right, moving on to reaction mechanisms. If I were to give you this reaction right here, just the H2, we generally think that it just happens like this. Like some H2 comes over and hits some ICl, and just like that, we get 2 HCl's and 1 I2, and that's not what happens. Oftentimes there are intermediate steps, and we're going to talk about those steps. They're called elementary steps, and they're steps that we assume occur. We say assume because there are various ways to get the same reaction to occur with made-up steps, but we'll talk about how that works here in a second, I guess. But essentially, most reactions can be broken down into individual steps. All right, in this particular reaction, we propose that step 1 is this, and step 2 is that. Now, it's important, and I just kind of rewrote them here. I don't know why they're written exactly the same thing. That these steps that you come up with, or you probably won't come up with them, but these steps that you're given, is important that they add up to equal the overall reaction that we were talking about, which is up here. So let's go ahead and add these two reactions up. HI is on both sides of the reaction, so it cancels. And I don't see anything else that's on both sides of the reaction. So when we go to add it up, we have an H2, we have 2 of these ICLs, we have 2 HCl's, and we have 1 I2. So we overall get the exact same reaction as we had up here. So all these elementary steps must add up to equal the overall reaction. Another thing is these things that get kind of crossed out, we call them intermediate reactants or reaction intermediates. And these are the things that are just kind of don't actually participate, but they were really important in making the reaction occur. All right. So elementary steps are characterized by the molecularity, so if there's one thing going to products, it's unimolecular. If it's 2, it's bimolecular. If it's another different 2, it's still it's bimolecular. You know where we're going with that. But what I think is more important is this. So if you're using an elementary step, the rate law is actually pretty straightforward to determine. We don't have to do experimental stuff like we've been doing in the previous sections, where we're looking at when something doubles, what happens to the rate, etc. Here, it's just based on the products. So my rate law here, if I've got an A, it's K times A. If I have 2 A's, it's K times A squared. If I have an A and a B, it's K times A times B. If it's got 3 A's, it's KA cubed. Hopefully you kind of see where we're going with this. And these are rare because it's rare that 3 things will orient perfectly and react, but nevertheless they do exist. And so it's kind of these trimolecular things are still important to look at. All right, so the important part being that we understand that we can write the rate law for these things without doing any experiments at all. They are just given for elementary steps. Okay. This is another really important thing to know, and one that will show up a lot. There are oftentimes 2 or more steps in a reaction, and it is the slowest step that determines the rate. So the slowest step is the one that we're going to look for to determine if to determine the rate law. So I'm going to actually write that. The rate determining step is the slowest elementary step in a reaction. It helps determine, not helps, it does. It determines the rate law. Okay. So this, when we started off a few minutes ago, we had just one single reactant that went to one single product. Now we have these intermediate steps. And notice that 1 is much higher, so this would be the first step of the reaction, and this little one would be the second step of the reaction. This one that is higher obviously required more energy. It's kind of the annoying one. And once you have that much energy, this next step can happen very quickly because you already have that energy there. It's like if you're going up the stairs and then running down the stairs is super easy, but going up the stairs is the hard part. That's what's going to happen slowly. And so this would be called the slow step. This whole reactance to your intermediate products right here. It's always given to you. It will tell you which one's slow or which one's fast. Or if you got a graph like this, you'd be able to figure out that the first step was slow and the second step was faster. But here's what I mean by it determines the rate law. Okay, there are two things we're going to look at right now. The first thing we want to look at is do the elementary steps add to the original reaction? So we're going to add them up and see if they get the overall reaction. And 2, does the slow step give the original rate law? In other words, experimentally determined rate law. Okay, so first, do the elementary steps add up? Next, does the slow step give us the original rate law? So let's talk about how that works. In this example, somebody proposed that these are the two elementary steps. Let's say we want to prove that this is correct. So in order to do that, we add these up and make sure that we get the original reaction back. This is the original one. All right, if I'm looking at this, I've got a couple intermediate reactants or reaction intermediates, the NO2 there and there. You could have chosen either one of those NO2s, and NO3 there and there. All right, although NO2 was a reaction intermediate, it was also a full reactant, but the NO3 was definitely a reaction intermediate. And so let's add these up. The stuff that didn't cancel, I got NO2 plus CO, yielding NO plus CO2. So again, step number 1 is, did these elementary steps add up to give us the original reaction? Well, the original reaction's right here, and it looks like it is exactly the same. So that's yes. Woohoo! Good job. Step number 2 says, does the slow step give the original rate law? So let's look at this slow step. Again, it would be told to you that this was slow. I'm going to rewrite it because I crossed some stuff out. We had NO2 plus NO2, yielding NO3, plus no. All right, if I asked you to write the rate law for this, much like in this thing we looked at over here, the rate law is not experimentally determined. We're just going to be multiplying them together. So, and by them I mean the reactants. So our rate law here would be rate equals K times NO2 times NO2. In other words, our rate equals K times NO2 squared. What was the experimentally determined rate law in this? It was K times NO2 squared. So we added them up and they got the original reaction, and we looked at the slow step, and lo and behold, the slow step's rate law equaled that of the overall reaction. And hopefully that should make some sense, because what actually determines how fast a reaction is going to go is the slowest part of that reaction. The rest is just easy as pie. Nothing's easy as pie, but hopefully you understand. All right, This is that fun one for those of you who are in class. You guys love this. Okay, so here I'm asking you to do the same thing. I want you to prove that one, the elementary steps sum up the overall reaction for some proposed elementary steps, and two, that the rate law that is predicted by it, in other words, particularly the slow, not particularly, the one that is predicted by the slow one is exactly the same as the overall rate of the reaction. So this is the reaction, and this is the rate. And we have to prove that these steps add up to give us this reaction, and that the slow rate gives us this rate of the overall reaction. We're going to start by doing, let's go ahead and start and make sure that they add up. Okay, so step number one, let's just add these suckers up. I look to see if anything cancels. I see the O cancels with that O. This is over here on the products, and this is on the reactant side, and that's why they cancel. And then I'm kind of left with 2O3. I don't see anything else that cancels. Yielding, and I got 2 O2s here, plus 1 there would be 3 O2s. So that was what we started with, and then when we added them up, we got that back. So that's good news. We're halfway there. All right, the second thing we have to prove is that this slow step is going to give us this rate law right there. All right, so in order to figure that out, I'm going to rewrite this, if you don't mind. We have O3, a little bit bigger. Going forward, and this one's the reverse. O2 plus O, and it said that this one was fast. And then we have O3 plus O, going with K2 to 2O2, and it says this one is slow. All right, so if we were to do a rate law for this, we just said rate equals K times O3 times O. And if you remember, the rate law we were trying to prove is this one right here, O3 squared, O2 to the -1, and at first glance, this is not the same. Obviously, this and this are not the same. However, we could look and say, okay, is there something I might be missing? We know that the rate law can't include O, right? There's no way it can include O because the overall reaction doesn't have O. That's a reactant intermediate. So let's see if we can get rid of that O by replacing it with something else. But where else is that O? The only other place I might see the O is in the fast one. So if we do the rate law for the fast one, it's rate equals K. There's two different reactions, by the way. There's a forward and there's the reverse. So let's do the forward. In the forward reaction, we have rate equals K times O3. That's going this way. In the reverse, we have the opposite. We have K, and this, sorry, I need to start labeling these. This was K2, this is K1. And the reverse, going this way, we have K -1, you can't see that negative very well, meaning the reversed K, times O2, times O. Now, if I solve for O here, I'd end up with something with a rate in the equation. And we don't want to end up with something with rate because we want to replace this O and we don't want to have two unknown rates. That can be kind of frustrating. And so instead, we're going to look at the rate relationship between a reaction going this way and a reaction going that way. If the rate of something going this way is a particular number, the rate in the reverse must be the same. As fast as this one's growing, this one has to be decomposing at the same rate. That is, by definition, equilibrium, so the rates are equivalent. So let's go ahead and set these rates equal to each other. The rate forward, so because rate forward equals rate reverse, we can set these things equal to each other. The rate forward was K1 times O3. I'm going to set that equal to the rate reversed, which is the K reverse O2 times O. Now to bring you back and remember what we're doing, because sometimes that helps, we are trying to prove that this rate law is the same as this. But we know that we can't include O. So we're trying to substitute O with something. So when we get down to here in this point, we need to get O alone. So we can substitute it back up in there. The way to get O alone is just divide by this K negative 1 times O2. And that gets O alone. In other words, O is equal to K1 O3 divided by K reverse O2. All right, so this whole thing is equal to my O, and I can replace it back up there. So let's do that. We have rate equals K2 times O3, and now this whole thing is going here. K1 times O3 over K reverse times O2. All right, now the beautiful thing, you have K2, K1, and K negative 1. You could just mush these all together. We don't know any of them, and we can just call them all K. K. K? K. All right, and now we just have an O3, an O3, and an O2. Well, if we push those together, that's K O3 squared over O2, which is the same thing as saying K O3 squared times O2 to the negative 1. So we took the slow rate, we realized we couldn't use O, we had to replace it with something. The only way to do it was what we did up here. But the beautiful thing is, this was the rate that we got. And this was the rate we were trying to prove. They are exactly the same thing, and therefore we did this one too. So we summed everything up and made sure it all added up, and we proved that the slow step rate law gave us exactly the same rate law back that the experimentally determined rate did. Whew. My favorite problem of the semester, for sure. All right. Last but not least, catalyst. We didn't spend a whole lot of time here. Mainly, catalysts increase the rate of the reaction, but they're not consumed in it. They do this by lowering the barrier energy, the activation energy. So, for example, ozone, O3, reacts with monoatomic oxygen, and it forms two O2s. And this happens at the ozone layer. This is essentially quote-unquote depletion of the ozone layer, and it happens very slowly. It takes a good amount of energy for it to occur. Doesn't really like to do it, so the ozone layer is actually relatively stable. This, by the way, is called ozone. But if you go ahead and add some chlorofluorocarbons to it, aka stuff that we make on Earth, like aerosols, etc., and they make their way up into the ozone layer, what they'll do, we'll just look at it as chlorine. They'll go through two steps. Whoops. ClO. I'll just rewrite it as ClO plus O2. So this is step 1. And then in step 2, you get this. Now, these are the elementary steps, proposed elementary steps for how this reaction happens. The Cl cancels, the ClO cancels, and if we add it up, we get back our original equation, O3 plus O, yielding 2O2. And notice that these reaction intermediates, the Cl and the ClO, normally we wouldn't really be too concerned about it, but here's the problem with them, is they reduce the energy required for this reaction to occur. And notice that at the end, they're not there, which means if you started with a certain amount of chlorine, at the end of this reaction, you still have that same amount of chlorine, and it can just continue to do this reaction over and over and over again, depleting the ozone layer. So the way it does it, this would be like our step 1, this would be our step 2. So normally it takes a lot of energy for the ozone layer to get depleted, but if we add this chlorine to it, it's no problem. It can do it very quickly. And again, the chlorine doesn't get used up, so it gets to continue to move through the atmosphere doing stuff. Catalytic converters, kind of the same way. If you've had a catalytic converter get stolen, the way they work is they have a certain metal like platinum or palladium or rhodium, and that metal helps reduce the amount of noxious fumes, bad fumes in the atmosphere, and it also helps utilize a little bit of leftover petroleum that might be in your gas tank. But yeah, so by taking away catalytic converters, we are polluting the atmosphere. So yep, I think that's about it. Sweet. Okay, so the main thing for a catalyst is just understand it's not consumed and it lowers the activation energy. All right, y'all. I think that is about it, and I hope you have a wonderful day. Bye.